Welcome to today's Explainer. We're jumping right into something you never see, but literally trust your life to every single time you step into an electric vehicle. We are diving into the invisible fortress, the life-saving engineering that stops catastrophic high-voltage EV failures dead in their tracks. It's an absolute masterclass in safety, and the tech behind it is just fascinating. Let's get right into it.
So you gotta wonder, what actually happens if that invisible high-voltage shield breaks? Well, in the engineering world, a breach triggers specific diagnostic trouble codes, namely P0AA6 and P0A7A. This right here is the lethal red line. It means the insulation barrier separating the lethal high voltage of the battery from the metal chassis, the actual frame you're sitting inside of, has completely collapsed.
To really understand how we're kept safe from that, we're going to walk chronologically through the 5 distinct layers of defense: the deadly red line, precise dynamic detection, physical defense design, zero-defect manufacturing, and finally, extreme validation testing.
Starting right off with Layer 1, the deadly red line, specifically looking at the failure mechanism, we need to figure out exactly what's threatening this protective high-voltage moat in the first place.
One of the absolute sneakiest threats out there is called electrochemical migration, or ECM. I want you to picture ECM as these microscopic metallic weeds growing across a circuit board. How on earth does that happen? Well, think about extreme temperature shifts causing condensation inside the battery box. Or say there's a micro leak of coolant from a tiny microscopic pore in a cold plate. That moisture mixes with the coolant, and under a constant, high direct current electric field, metal ions actually dissolve. They start migrating. Over time, they grow into these tiny metallic dendrites, those weeds I mentioned, and eventually those weeds bridge the gap between the high-voltage conductor and the low-voltage chassis. The result? A massive and potentially lethal short circuit.
But hey, the threat isn't just those internal metallic weeds. External components can fail on us too. Take the high-voltage AC compressor. It can literally age and degrade under extreme heat. Or the ceramic plates in your electric cabin heater could suffer a thermal breakdown. And we can't forget physical mechanical threats. Imagine a thick, high-voltage wire harness physically rubbing against a sharp metal chassis edge. All that high-frequency road vibration, day after day. Over time, that vibration wears the insulation right down to the bare metal, leaving a live wire completely exposed to the frame of your car.
And that brings us to line 1, precise dynamic detection.
Because we know these threats are out there, the vehicle's battery management system, or BMS, has to act like a real-time, ultra-precise radar. Hardware and software are working in perfect harmony here. There's a physical insulation monitoring device that actively injects these specific low-frequency sine waves into the system. See, traditional detection methods get totally confused by all the intense, high-frequency electrical noise buzzing around from the motor's power switches. But this system, the software's multi-frequency filters cut through all that background noise to perfectly isolate any actual real-world insulation threats.
Now, if the hardware spots a leak, the software kicks in as the ultimate global safety layer. It has to react dynamically based on how bad the leak is. If the insulation drops to somewhere between 500 and 100 ohms per volt, it triggers limp-home mode. It doesn't just abruptly kill your engine on the highway. That would be incredibly dangerous. Instead, it reduces power and shuts off unnecessary high-voltage loads so you can safely pull over. But if there's a severe insulation collapse, meaning it drops below 100 ohms per volt, the system immediately enters safe state. In a fraction of a second, it severs the main contactors to physically isolate that high-voltage battery, literally saving your life. Moving on to line 2, physical defense design. Because catching a failure is great, but how do engineers blueprint the fortress to stop it from happening at all? This all goes down in the design FMEA, the failure mode and effects analysis phase.
Design engineers come up with some seriously brilliant preventative designs here. First, there's 3D physical isolation. That basically means routing the coolant paths as far away from exposed high-voltage copper bus bars as possible, so a leak can't just drip onto a live wire. Simple, but effective. Then they use IP68 Gore valves. These are specialized, breathable valves that let the battery equalize pressure without letting a single drop of water in, stopping that dangerous condensation we talked about earlier. They also wrap wires in thick, high-rigidity double-layered harnesses to fight friction. Oh, and here's a cool one. They add smart software logic with a 2 to 5 second debounce window. Basically, if you drive through a massive puddle and a splash temporarily drops the insulation resistance, the car waits a few seconds to double-check the threat. That way, a harmless puddle doesn't shut down your EV right in the fast lane.
Next up, we advance to the assembly phase with Line 3 zero-defect manufacturing.
The goal during the process FMEA phase is mind-boggling. Ensure millions of components are built with absolutely zero microscopic flaws. To pull this off, the assembly lines use automated, dual high-resolution cameras to visually inspect every single millimeter of structural glue and brazing. No room for error. At the end of the line, they run microscopic helium leak tests. Helium molecules are incredibly tiny, so the logic is, if helium can't escape, water definitely isn't getting in. And as a final touch, they use vacuum technology to apply a highly dense conformal coating across all the circuit boards. It essentially vacuum seals those fragile electronics, making sure those metallic ECM weeds never even get a chance to take root.
Which brings us to our final line, extreme validation testing. Before any of this tech makes it to your driveway, it has to survive the absolutely brutal DVPNR torture tests.
First on the chopping block is the AC injection test. Engineers take the detection software and absolutely blast it with 20 kHz of electromagnetic motor noise, just massive electronic chaos. And while that's happening, they trigger a simultaneous symmetrical leak on both the positive and negative wires. The system has to prove it can spot that perfectly balanced leak in under 5 seconds, without a single false reading or diagnostic blind spot. Talk about pressure.
Then comes the double 85 test, which sounds awful, and it is. To guarantee zero dendrite growth over the car's entire lifespan, they bake the circuit boards in an environmental chamber at 85 degrees Celsius with a sweltering 95% humidity. And they don't just leave them sitting there, they continuously pump them with 800 volts of DC power for 500 continuous hours. Throughout all of this, the leakage current is strictly monitored and it cannot exceed a single milliamp, not even once.
And the torture just keeps going. Up next is 300 hours of structural fatigue testing. Fully assembled battery packs are strapped to a table and put through violent, random 3D shaking, all while the temperature rapidly cycles from a freezing -40 to a scorching positive 85 degrees Celsius. It's designed to stress the metals to their absolute limit. After all that thermal shock and shaking, the pack undergoes yet another helium test just to guarantee that the IP68 waterproof seal is still 100% perfectly intact.
Finally, we hit the ultimate checkpoint, the Hipot test. Every single finished battery pack rolling off the line gets deliberately blasted with 2,500 volts of pure DC power for 60 seconds straight. If it leaks even 1 milliamp, if there is the tiniest micro crack or just a slightly pinched wire, it is rigidly intercepted and immediately scrapped, period. It never leaves the factory.
So this incredible 5-layer fortress of detection, design, manufacturing, and testing is what's protecting you every single time you drive an EV. But honestly, mastering all of this leaves us with a really fascinating final question. What exactly happens when these insulation failures interact with the main high-voltage contactors? Like, could an insulation crash actually cause the main relays to physically weld shut, making it impossible to turn the car off? Well, that is a completely different, thrilling engineering challenge, specifically code P0AA1, and it's exactly what we're going to explore in our next explainer. Thanks so much for joining me today, and keep learning.